So let's talk about what physically happening during the interface flux. Suppose we have a fluid flowing over a flat plate. Now due to the no-slip boundary condition, the fluid particles that are in direct contact with the surface of plate come to complete stop. They have zero velocity.
Right, and just around the first layer, the next layer of the fluid is moving, but it is slower than the free stream. So between the surface and the outer fluid, there is a gradual change in velocity from zero at the surface to full velocity of fluid far away from the wall.
This variation in velocity with respect to distance from the surface forms what called a velocity gradient. And the region where the gradient exists is the boundary layer. Within this layer, faster moving molecules transfer momentum to the slower ones below them, layer by layer.
This continuous transfer of momentum between fluid layers is what we call the momentum flux. It's not just an abstract idea, this is exactly the reason why we observe the shear stress at the wall. The fluid is resisting the change in motion caused by the solid surface, and that resistance is felt as drag on the surface.
And what's fascinating is that this mechanism of transfer caused by a gradient is not just limited to momentum. The same idea applies to heat and mass transfer as well.
Take heat transfer for example. Imagine the same plate is now heated. The temperature of the surface is higher than the temperature of the fluid far away. That creates a temperature gradient across the boundary layer.
Molecules near the hot surface observe the thermal energy. These energetic molecules then collide with the neighboring cooler ones, passing on their energies. This is how thermal energy moves from surface to the fluid. This is heat flux.
Now in mass transfer, it's a similar story. So the plate has a higher concentration of the chemical species like water vapor or ammonia, and the surrounding fluid has a lower concentration. That concentration difference creates a concentration gradient.
Molecules naturally diffuses from region of high concentration to low concentration. So from surface where the concentration is high, molecules move out into the fluid. That's mass flux. And again, it's driven by the gradient.
Whether it's velocity, temperature, or concentration, the idea remains the same. When there is a difference across the interface, nature tries to even it out by transferring momentum, heat, or mass. This is what we call the interface flux.
The interface, the point where two phases meet, like solid and fluid, is the exact location where the gradient exists and where the transfer happens. It's the zone of action.
Mathematically, we represent these transfers using quantities like tau w, shear stress at the wall, qw, heat flux, or Na, the mass flux. Each of these is proportional to the respective gradient at the wall. Shear stress is proportional to velocity gradient, heat flux is proportional to temperature gradient, and mass flux is proportional to the concentration gradient.
And these gradients are typically steepest right at the wall because that's where the changes happen most sharply. So understanding the behavior of fluid in this thin layer near the wall is critical in engineering design.
It also explains why engineers use dimensionless numbers like Reynolds number, Nusselt number, and Sherwood number to characterize the nature of the flow, the thickness of the boundary layer, and the relative importance of the convection versus diffusion.
In practical terms, the interface flux determines how much cooling is needed in an engine, how much drag a car feels, how fast a medicine spreads in the bloodstream, or how efficiently a reactor performs.
So while it starts with gradients at a microscopic level, the effects are visible in almost every real-world system involving the fluid flow and the transfer.
And that thoughts make us understanding interface flux essentials, not just theoretically, but for everything from aerospace to chemical processing to environmental.
Now we'll start with the physical interpretation. Physical interpretation. Physical interpretation. Interpretation of friction factor. Okay. So let's start with the basic formula. What is the basic formula of tau w? Tau w equals to tau yx at y equals to 0. We get mu dou vx upon dou y at y equals to 0. Then another formula of tau w, that is half rho V infinite square into, right? This is equation 1 and this is equation 2. Now let's combine equation 1 and 2. Combining equation 1 and 2, we get half rho V infinite square into F equals to mu dou Vx upon dou Y at Y equals to 0, right? So let's take V infinity on the right hand side. So we will get half rho V infinite into friction factor equals to mu by V infinite into dou Vx upon dou Y at Y equals to 0, right? Now let's draw the velocity distribution curve for this equation. We have this as our flat plate. Okay. Now we have the curve like this. This is the velocity distribution curve, the velocity distribution curve, distribution. Okay. And the slope of this curve is given by dou Vx, the slope is given by dou Vx upon dou Y at Y equals to 0. We have film thickness or laminar film thickness delta, right? So this is the ideal case. The actual case will be, for this case, for this momentum transfer thing, is, say this is our delta, the laminar film thickness. Delta is our laminar film thickness. Laminar film thickness. This is our graph. We are having at this point V infinite is increasing linearly, then we have a constant V, and the slope is dou Vx upon dou Y at Y equals to 0 equals to V infinite upon delta. We will prove this thing now. How we are getting this thing? So we have the equation half rho V infinite into F equals to mu upon V infinite dou Vx upon dou Y, right? It is equals to at Y equals to 0. So we can write dou Vx, this is equation 3. We can write dou Vx dou Y from the above graph, from this thing, we can write this as at Y equals to 0, that is equals to V infinite upon delta, that is equation 4. Now let's combine equation 3 and 4. Combining equation 3 and equation 4, what we get? Half rho V infinite into F friction factor equals to mu upon delta. Now let's rearrange this equation. Rearranging the equation, we get 1 by delta equals to half F V infinite into rho by mu, right? Now we are multiplying both sides by LCH. What do we get by multiplying both sides by LCH? We get half F V infinite into rho into LCH divided by mu equals to LCH upon delta. So from here we can write half F into RE equals to LCH upon delta, where RE equals to LCH V infinite into rho by mu. and this RE is our Reynolds number. This is the physical interpretation of friction factor. I hope you have understand this well. Now we'll solve a question, a problem. The problem says in a fluid flow over a flat plate, over the flat plate. The following given data is friction factor as 0.04, V infinite, that is characteristic velocity as 2.5 meter per second. We have characteristic length LCH as 0.5, rho as 1000, 0.5 meter, rho as 1000 kg per meter cube, and dynamic viscosity, that is mu as 0.001 Pascal seconds. Right? Now we need to calculate A, the Reynolds number, calculate the Reynolds number, RE, and also the boundary layer thickness. Boundary layer thickness. So let's solve this problem one by one. Starting with the Reynolds number. What is Reynolds number? What is the formula of Reynolds number? As shown previously, Reynolds number is equals to LCH V infinite into rho by mu, right? So RE is equals to 0.5 into 2.5 into 1000 divided by 0.001. Please check the units. So we will get this as 1250 into 0.001. That is 125000. This is our Reynolds number. Now we need to find the boundary layer thickness. We know the boundary layer thickness is half F RE into equals to LCH by delta, where delta is our boundary layer thickness, right? So let's rearrange and find out delta. Delta is equals to LCH half into friction factor into RE. So let's calculate. LCH is 0.5, half into 0.04 into 125000. So Reynolds number. So while calculating, we'll get this as 2 into 10 to the power minus 5 meter equals to 0.02 millimeter. So we get our boundary layer thickness as 0.05 millimeter and our Reynolds number as 12,50,000. Thank you.